In this video, we will once again continue on our discussion of the strategies of integration. So recall, if you look at an integral, you immediately recognize how to evaluate it or the technique that applies, you do so. If not, these strategies give you a few mental checkpoints to go through. So is it something that is a common integral, or if not, can you get to it through some algebraic simplification? Look for obvious substitutions or things where we can apply the typical methods that we've learned. Trigonometric integrals, trig substitutions, integration by parts, partial fraction decompositions. If not, we sometimes have to go a bit further. So for the integral that we're given here, e to the square root of x, there's no algebraic simplification, no obvious substitutions, and none of our techniques of integration really apply to this conveniently. So instead we could ask, is there a more subtle substitution? And if we think back to the rational substitutions we've discussed, if we say w equal to the square root of x, we will eliminate the square root term in our integral, and hopefully what results will be simpler to evaluate. So if w is equal to the square root of x, this is equivalent to saying x is equal to w squared. So that dx is equal to 2w dw. So putting this integral solely in terms of w, we'll have the integral of e to the w times 2w dw. 2 is a constant that pulls out front, and what we're left with is w e to the w dw. And this is a common type of integral. Whenever we see a polynomial times an exponential, we should recall that that is well suited for integration by parts. So with the integration by parts, we would want to choose our u to be w, and we would choose the dv to be e to the w. So du is just dw, and v is e to the w. And integration by parts tells us uv minus the integral of v du. So we have the 2 hanging around out front, and we'll have uv, so w e to the w, minus the integral of v du. So distributing the 2 and evaluating our integral, we have the following. And our last step is to simply get back in terms of that original variable x. So each w that we see should get replaced with a square root of x. So 2 square root of x, e to the square root of x, minus 2e to the square root of x, plus c. So keep in mind, if you see those terms involving square roots and square roots of a linear term, a rationalized substitution can be applied to eliminate that radical from the integral. So one last example involving strategies of integration. And this is a rather difficult example, at least in terms of getting started. So based upon our integrand, it does not compare to any of the formulas in our table. There's no obvious substitution. It does not fit any of our standard forms. I don't see a more subtle substitution, but I think I could jump maybe to the step of doing some more advanced manipulation. What I'm going to do here is multiply by 1 in a fancy way, and this is maybe somewhat reminiscent to what we've seen in the past in Calculus 1 dealing with limits. So I'm going to think of this function as being the square root of 1 minus x over the square root of 1 plus x. And looking at the denominator, the 1 plus x under the square root, I'm going to multiply by its reciprocal. So square root 1 minus x, square root 1 minus x. So as indicated, this type of thing we have done in the past. Think conjugate over conjugates when dealing with limits. And the reason this works out nicely is in the denominator, you would have the square root, and we combine together the 1 plus x times 1 minus x. So that's 1 minus x squared. And in the numerator, the square root of 1 minus x times the square root of 1 minus x is simply 1 minus x. So this becomes the integral of 1 over the square root of 1 minus x squared plus the integral of minus x over the square root of 1 minus x squared. And this is the point where we see why this initial step of multiplying by 1 is going to work out so well. The first antiderivative is a common integral whose formula we know. This is arcsine of x. And the second integral is one that we see a technique of integration that clearly applies to it. We can use a obvious substitution, 1 minus x squared. So kind of a bit of advice or something to keep in mind is when you're looking at an integral, it may not immediately be obvious what type of manipulation will work. So sometimes you might have to try 2 or 3 things, maybe more or less, to find something that works. So do not be afraid to try something. If it doesn't work, cross it off, get a new sheet of paper, and at least you now know that technique of integration is not going to apply. So what I'm going to do here, just in terms of seeing the substitution, I'm going to put a 2 in the top and a 2 in the bottom, multiply by 1 in a fancy way. So if u is equal to 1 minus x squared, du is minus 2x dx. So this becomes plus the integral 1 over 2 square root of u du. And once we've multiplied by that 2 over 2, it works out very well because the antiderivative of 1 over 2 square root u is the square root of u. And if we resubstitute back in, we're left with arcsine of x plus the square root of 1 minus x squared plus c. And I would like to finish this video with kind of just a general observation. Remember, we've previously mentioned, differentiation is typically a much simpler process. It's very systematic. Based upon the function or its form, you know exactly what method of differentiation to apply. Integration, as we've seen, especially with this example, that is very clearly not the case. There are some integrals that you will encounter that might take quite a bit of time or quite a bit of thought to come up with that desired method. So remember to go through your mental list of strategies, and if nothing applies and you're trying to manipulate, don't be afraid to try multiple methods of integration.